हेलो। हाँ, तो ठीक, आप मुझे लॉकेट में डाल दीजिए। हाँ हाँ, स्टार्ट में डाल दीजिए। या आई थिंक इट्स ऑनलाइन नाउ, नो? या ओके। हाँ सर। So good evening to all the esteemed members of the Ocean Society of India, ladies and gentlemen. As we know that this Ocean Society of India, it conducts invited talks as part of the OSI webinar series once in every month. And this talk is arranged from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, and allied disciplines. And this webinar series is mainly targeted for students, researchers, scientists, engineers, and working professionals in the field of atmospheric, oceanic sciences, ocean engineering and technology, with a motive to impart and improve the knowledge benefiting the OSA community. I request all the members to actively participate and get involved in all the lectures under the OSA webinar series that will be held once in every month. On behalf of the Ocean Society of India, it is my proud privilege to welcome today Professor Manas Ranjan Behera, Associate Professor, the Department of Civil Engineering, IIT Bombay, for this invited talk today. So Professor Manas Ranjan Behera will be delivering a talk on the topic, the future perspective on coastal vulnerability and resilient infrastructure, which is a topic of relevance for scientists and engineers working in the field of oceanography, ocean engineering, and allied areas. So Professor Manas Ranjan Behera is a faculty of ocean engineering at the Department of Civil Engineering, IIT Bombay, and he completed his BTech honors with gold medal in civil engineering at VSS UT Odisha. And thereafter, the MS and PhD degrees in ocean engineering from IIT Madras. He worked at the National University of Singapore and the University of Edinburgh, UK, before joining IIT Bombay. His research interests are on different areas like coastal hydrodynamics, coastal hydro-morphodynamics, climate change impacts on coastal vulnerability and risk, extreme waves, which includes storms and tsunamis, the impact of these extreme waves on offshore and coastal infrastructure, etc. So Professor Manas Ranjan Behera specializes in the area of computational ocean and coastal hydrodynamics, coastal flood modeling in a changing climate scenario, longshore sediment transport, and coastal morphodynamics, resilient coastal infrastructure under extreme ocean waves, and ocean renewable energy. So he has published more than 125 research articles in high impact international journals and peer-reviewed conference proceedings. He has supervised 8 postdoctoral fellows, 7 PhD students, and 15 master's students. And currently, he is supervising 2 postdoctoral fellows, 7 PhD students, and 1 master's student. He has also served as the editorial board member and guest editor for referred journals. He has initiated several national and international research collaborations, and he received the prestigious Professor J Garde Research Award 2018 by the Indian Society of Hydraulics, recognizing the contributions in the field of ocean and coastal engineering. In addition, he has also received several awards, honors, and recognition. He has extended the professional activities for various academic, research, and industrial organizations. And he has also extensively contributed to administrative responsibilities at the national and institute levels. Currently, he is leading a research group on coastal, ocean, and climate sciences at IIT Bombay. Professor Manas Ranjan Behera is a member of the International Water Association, a life member of the Indian Society for Hydraulics, a member for the International Association for Hydro-Environmental Research, Engineering and Research, member of the American Society of Civil Engineers, member of the American Society of Mechanical Engineers. He is also a member of the Coastal Zone Management Sectional Committee of the Bureau of Indian Standards, a member of Technical Advisory Committee of Maharashtra Maritime Board, a member of the Technical Advisory Committee of the Indian Register of Shipping. He is very active in many research projects, national and international research projects. And so with this brief introduction, it is my proud privilege to kindly invite our speaker for today, Professor Manas Ranjan Behera, to deliver the talk. The participants are requested that the questions and answers session will be attended after completing the talk, and the questions can be messaged for the speaker in the chat box. Thank you. So now I request Professor Manas Ranjan Behera to please deliver the talk. Manas. Okay, fine. Thank you. So I think Professor Manas is having some network issue. He's trying to connect again. So he'll be back soon. Yeah. Hello. Yeah, it is online in the YouTube. So Manas is actually having some network issue. He's trying to reconnect again. Yeah. Yes, Professor Manas.
Sorry, sir, and
no problem, no problem. You can start actually.
Just wanted to check if my presentation is visible.
Yes, it is visible. Yeah, it is perfect.
Okay, so extremely sorry that due to this internet glitch, I got logged out just at the end of your introductory introduction. So let me, can I start, Professor Bhaskaran?
Yes, please, please.
Okay. Thank you, Professor Prasad Bhaskaran, for your kind words. And I would also like to take this opportunity to thank Ocean Society of India. I think I have not possibly mentioned in that profile that I have given you, but I am also a member of Ocean Society of India. I take pride of being a member in that society. And let me quickly start without further delay on the topic that we are going to talk today, that is future perspective on coastal vulnerability and resilient infrastructure. So the reason why I wanted to speak on this, because in the recent past of in the few years, we have been observing many coastal hazards, and there are a lot of coastal stresses which are affecting the coastal community. So we need to think in that line, and we need to be prepared for future how we can protect and be prepared for the coastal hazards that are going to affect us. And especially when we talk about coastal urban cities, they are highly vulnerable. So in general, the coastal vulnerability and the resilient infrastructure needs tremendous focus at the current state. So looking at various coastal vulnerability stresses, if we see, there are a number of events that are going on. First one, we all know that there is wave which is there along the coast, and that is coming and going. We realize or not, it is affecting, or it is having some impact on the coastal ecosystem that we have. I will talk more about that possibly later. But in addition, when we have these waves, due to certain characteristics of the waves, we may encounter erosion or accretion or deposition, I would say, at some location. So this erosion and deposition both are equally having negative impacts for various purposes. If there is erosion, there could be loss of land. If there is accretion or deposition, there is possibly some kind of inconvenience for various facilities that we have, something like ports and harbors or various coastal other facilities might also get affected. So we need to be bothered about that. Next, there is a talk about sea level rise. IPCC has already mentioned in IR6, in AR6, it is already mentioned that sea level rise has impacted various locations, especially the low-lying areas are going to be highly impacted. So there is a need for thrust in this area as well. Next, we have cyclones, which are perennial problem for country like us, and especially we have been seeing cyclones along the east coast of India every year, at least once or twice, mostly during pre-monsoon or post-monsoon seasons. But over the years, we have seen that the intensities have increased, or the kind of stronger cyclones have become more and more over the past years. So it is essential that we track the cyclones properly. We also predict the cyclone associated other disasters like storm surge as much as possible in an accurate manner, and that way we can reduce the damage that can happen. So storm surge flooding is another important aspect which can also inundate huge coastal areas and affect the coastal communities and their livelihood. So we need to be prepared for all that. Next, tsunami, although we had the last tsunami in India in 2004, but the recurrence of this event cannot be ruled out. And when we have been living in a place that is completely open to the tsunami or earthquake prone regions where the tsunami can be generated, so we have to be prepared. So last tsunami which happened in Sumatra coast, so that same coast can also trigger another tsunami at any point of time, and we may be vulnerable. In addition, there are other locations from where the tsunami can also come. So we need to be prepared for all these events that are going to be coming to the coast. Next, coastal infrastructure. As I have been talking about that in the first slide, that we need to prepare our coastal infrastructure. So although we are talking about all these coastal stressors or vulnerabilities, but at the same time, whether our coastal infrastructure are ready or equipped to handle such kind of disasters or such kind of forces that are coming from the coast. So that also needs more importance and more thrust in the coming days. Finally, nevertheless, coastal water quality also has very, very strong role to play in the coastal resources. Because if you look at this slide that I'm showing on the right side, you can see the dark patch that is very close to the coast, and you see slightly south and north of that, you don't see that dark patch. So if you go to the simple normal Google search engine, Google Maps, if you track the historical images, you can see that over the years, this place has been polluted. So we need to figure out why this pollution is happening, and if this kind of pollution happens, what are the impacts on the coastal whether you call it vegetation or life or whatever it is. There could be fish, there could be coastal vegetation or whatever it is. So what is the impact of that? I'm not even bringing the tourism. Tourism is also going to be highly impacted if such kind of coastal water quality is going to be affected. So we need to be concerned about that. Now, having said all this, I'm not possibly going to focus everything in this talk. I'll try to focus mostly on the cyclone generated storm surge and its impact along the coast, as well as I'll talk about slightly on the waves, how the waves are going to change in the future scenarios and what will be its impact and how we can be ready for that. So coming to the cyclones, if we look at the number of cyclones that are occurring along the coast, we can see that there are huge number of cyclones that occur along the east coast of India, and there are also some cyclones which are recorded along the west coast of India. And among those cyclones, there are some cyclones which are hitting the west coast of India. So if we look at those, there is significant amount of concern or cyclones that are occurring. And if you look at the right side figure, you can see at a particular time, there were two cyclones simultaneously in both the basins. So one cyclone, that is Titli, which was hitting the east coast of India, and same time there was one cyclone Luban, which was there along the west coast of India. So it basically indicates that sometimes the ocean releases so much of energy that these cyclones do occur, and it may occur simultaneously along both the coasts. So if we are affected by both the coast from both the coasts, then what is our preparedness? How we will be ready for that? And whether we are really focusing or predicting this cyclones properly, whether we are predicting this cyclonic surge properly, that is the concern. So if you look at the statistics, see, along all the ocean basins, Northern Indian Ocean only encounters 6% of the cyclone, and out of that, Bay of Bengal has 4% and Arabian Sea has 2%. So it is a very small number. But given that small number, this 6% of the cyclones in the North Indian Ocean basin leads to 80% of the global fatalities, which are mostly due to the coastal flooding. The cyclone generated rainfall, surge, these two parameters are leading to the coastal flooding, and they are affecting 80% of the global fatalities. So fatalities is not necessarily only the deaths, it can lead to all other effects that it's bringing, or the cyclone is bringing along with it. So when we are talking about it, we also looked at how in the past the cyclones were there in the North Indian Ocean basin and how it has evolved over the decades. Now, if you look at this figure, shows the Atlantic Ocean basin, and we can see that the energy, there is something called PDI, power dissipative index, which is a function of velocity, or the cyclonic wind speed, we call it maximum sustained wind speed, Vmax. So that maximum velocity is governing what is the power dissipative index. And by that, we could see that enormous power is present in other ocean basins. But when we come to the North Indian Ocean Basin, this energy was comparatively lower, but there could be various other reasons. But over the last decade, we could see that the increase in the power dissipative index. So that means the intensities have been increasing in the last several years. And that is seen in both Arabian Sea as well as Bay of Bengal. So there is a need for understanding how these cyclones are going to be tracked, or how well we can represent these cyclonic parameters. So looking at the damages that they do, the devastation that they occur, they create, you can see here different cyclones starting from super cyclone in 1999. The damages are severe, and even the cyclone Titli that I referred to, that has also affected severely along the coastal regions of Odisha. So having seen this kind of damages, we need to also understand what are the factors or parameters that are affecting or that are driving this cyclonic surge. So what is surge? First of all, surge is nothing but an abnormal rise or fall of water level in the sea that is generated by the tropical storms over and above the astronomical tide. Tide is something which is always there. So this surge, when it comes above the astronomical tide, and that pushes into the landmass and it affects the coastal region, leading to flooding. So what are the factors that are affecting? If we look at, there are a number of factors. First one, if I start with, the major or important parameter is just storm intensity or wind stress, or rather in layman term, we can call it wind speed. So that is the first and foremost important parameter. In addition, there are a lot of other parameters. What is the central pressure, or we call it depression? That is, what is the depression in the pressure with respect to the ambient pressure around the region? And then what is the storm size, how big it is, with what speed it is moving forward, with what angle it is affecting the attacking the coast, what is the coastal geometry? Sometimes we may have a shallow coastal region, we may have a deeper coastal region, so that will also have some impact. Then finally, we also have regular or ambient condition of sea and swell, which are already there in the ocean, which is present. So what is the effect of that in addition to the perennial tide which is present? All this lead to the eventual surge that is going to take place. So how do we talk about it? So instead of going to all that, I will try to focus only on a couple of parameters. I'll try to go on to the wind stress, or we call it cyclonic wind speed, Vmax, maximum wind speed. So when we talk about it, that wind speed is the major driving parameter which is going to impart the energy from the air or atmosphere to the water or sea surface. So how it basically is governed? It is governed by the drag that takes place along the surface. And this drag, I think, I'm sorry, there should be 1/2 here, 1/2 rho CD U square. So irrespective of that, now the CD, when we are talking about the drag coefficient, earlier various researchers have worked on that, and they have represented this value of CD mostly linear way. So, or the variation is linear, that we can see. Here mostly the variations are linear in this graph, and at some point people realized that it's not really going to increase or keep on increasing with the wind speed. It will possibly stop at certain point. So they have given a cutoff value. So you can see here there is a cutoff value of wind drag coefficient. So beyond wind speed of approximately, let us say here it's around 30, the wind speed is expected, or the drag coefficient is not expected to increase with the increase in wind speed. But if you see this bars, which is basically a field survey which was done by Sondes, and the drag coefficients were obtained during an actual cyclonic event by flying aircrafts above that. So the data that was obtained shows that the wind, the drag coefficient does not increase linearly. It does not remain as a constant value after certain wind speed or cutoff is there. Rather, it is decreasing beyond certain point. So that basically indicates that there is some internal process which is still going on, which can be represented to define the value of this drag coefficient, or the coefficient which is basically transferring the energy from air to sea. So having said that, there are a number of models which have been developed. One in 2004 that is called wave boundary layer model based on the wave boundary layer equation. And similarly, that same equation was again modified or enhanced in 2016. And this equation basically presents or considers the processes that are taking place at the boundary layer between the air and sea, or the air-sea interface. So that process is represented in this figure. You can see that there are number of processes that are taking place. You have turbulent stress, you have sea spray effect, you have wave stress that are going to come. You will also have the viscous sublayer which is going to be present. But the contribution of viscous sublayer could be very, very less when you have strong winds. But these other three are going to play a major role. So when we have this, how it can be represented? It is represented by this wave boundary layer model. And in that model, I'm not going to go to the equations and all. Anyone is interested, they can go to the publications and refer that. I will possibly show the publication later. So in this model, it is represented. And finally, what we get the value of drag coefficient, which is being used in the circulation and wave model. In this case, I have just mentioned ADSIRC and SWAN, but it could be any circulation and wave model that can be used. So if we use this, then what will happen? We will be able to update, or we will be able to use the more appropriate drag coefficient that will give us a better result. So what has been done? We have first got these values, or we have got the wave spectrum from this coupled model, and that wave spectrum is given as a feedback or input to this wave boundary layer model. And from that, we got the revised value of CD, and that is given to this again circulation and wave model. Finally, we get the output. So in this process, what we observed that we could really capture the significant wave heights as well as maximum water levels very well along the coastal locations as well as in the deep water locations. And we have tested it for two different cyclones. And we could see that, you see here, the comparison of the water levels. Here you can see here, this is water level elevation, and the locations are Ennore and Nagapattinam for two different cyclones. One is Cyclone Thane, that is in 2011, Cyclone Varda that occurred in 2016. So both the cyclones, we could get a very good result using wave boundary layer model compared to all other models. However, when we went ahead and checked it at deep water location is here, that is BD11, you see. And we also looked at the wave rider buoy at Pondicherry. If we see at the deep water location, the significant wave heights are not really captured. This black line shows the red observations, whereas wave boundary layer model output is quite far away of that. And same way, we also looked at another cyclone, and that also is more or less similar. And similarly, when we looked at the coastal locations, it matches. When the cyclone has a landfall, which is around 30th of December, we got a very good match. That means when the cyclone comes towards the coast, or when the cyclone is close to the location where we are observing, then we find a very good result. But before that, the results are not really good. So we wanted to understand why is happening. So that is another work, but this, whatever I presented so far, that was published in this journal in Ocean Engineering. Anyone who is interested to understand more can possibly refer this journal and get a detailed understanding. Now, the effect that we saw, we understood that it could be due to the pre-existing wave climate. So we wanted to consider the pre-existing wave climate into this modeling. So for that, we needed to consider the larger domain. We considered this bigger domain, and that we first simulated, and then this output of that is wave and swell, that is given as input to this nested domain boundary, which is shown here. And then we could really consider the pre-existing wave or sea and swell conditions, and that was taken into account. By taking that into account, we observed that the significant wave heights have significantly improved. You can see here, without considering the wave boundary condition that shows the red line is not able to capture, whereas when we considered with wave boundary condition, it is captured properly. And same thing is also observed for mean wave period, and wave period is substantially improved. And now when we looked at the wave direction, we found that there is a significant improvement in the wave direction. And why it is important? Because when we talk about this extreme wave impacts on various offshore structures or coastal structures, we need these values of wave height, wave direction, wave period. And if they are not really captured by these models, then we will not be able to predict the wave forces on those structures. So that is why it is very, very important. And that we have already demonstrated that the pre-existing wave climate must be accounted in numerical modeling of storm cells. Now, moving forward, we wanted the wave boundary layer model that I just talked about. We wanted to ensure that this model can be used for real-time predictions. And with this wave boundary layer model, it can possibly take quite a long time and may not be feasible to use it for real-time predictions. So what we did, we simulated a number of cyclones, almost 30 cyclones we considered from different ocean basins. And we also ensured that these cyclones represent different wind speeds starting from 30 meter per second to all the way 90 meter per second. We represented all different wind speeds, and that we simulated using this wave boundary layer model. And the output what we got, we used it to find out the best fits or the regression analysis we did, and we observed that the third order fit is the best suitable one that we can consider. So the third order best fits curve is given by this equation, and this equation we have designated it as improved wind drag method. And this work has been again published in this dynamics and atmospheres, dynamics of atmospheres and oceans. One can always refer that. So after developing this equation, we incorporated this into the source code of ADSARC and SWAN. And obviously, I'm not showing all the equations. So in these equations, we have incorporated these values of CD, and that we have taken for further analysis of number of cyclones. So that we considered for 2 cyclones in the Gulf of Mexico. We wanted to consider some more stronger cyclones, that is Hurricane Katrina and Rita. And when we simulated, we could observe that the outputs are very well matching with the observations. And that is again much better compared to all other models. So let us not get into that. But overall, what I wanted to convey is that we have developed this model, which is now working well till a wind speed of 90 meter per second. That means we can even accurately capture the conditions of supercyclonic storms or Hurricane 5 category or anything of that order. So those wind speeds are also very well represented in the models now. And when we see that this IWD method, whatever we have developed, they are really performing very well compared to all other models. Now that model, we also checked what is the time or computational time. So we found that if we use this wave boundary layer model, the computational time could have increased 2.5 times almost. Whereas in the real-time prediction, whatever we are using right now, we can still use that same amount of time, and we can use this IWD method and get the improved output from the models. So that's basically something which will be useful in future when we receive more stronger cyclones frequently, and our forecast is not going to be missed. Now, in addition, as I told you, different parameters can affect. And when the cyclone approaches the coast, it is also important to understand which direction the cyclone is approaching and what will be the impact. There are the physics or the dynamics of the circulation can completely change depending on the angle of approach of the cyclone. So we actually considered number of different approaches for a typical cyclone, and we found that when they propagate over different path, what happens? They encounter different type of bathymetry, and that can affect the process, or that can affect the physical process that is taking place in the ocean. And in addition, depending on the shape of the coast, whether it is concave coast or convex coast, the physics could be completely different. And we observed that the maximum surge could occur in a concave coast if the cyclone is going to approach at an angle of 75 degrees. And this can possibly change if we move to another domain or different coast, let us say west coast. This could be slightly different because the dynamics will be different. but along the east coast, we found that this is what is going to happen. So these are very, very important to understand and know, so that we can predict for future. In addition, the cyclones, how they intensify. The cyclones intensification can be completely different. They can intensify in the deep ocean, or they can intensify and become peak when they're approaching the coast. It can completely vary. So we wanted to understand that. And when we analyzed all different cyclones, you can see here number of historical cyclones in the Bay of Bengal from 1982 to 2020 we analyzed, and we found that intensification period varies. Sometimes it is varying. Zero is basically as you move on the right side, it is the time before landfall, and on the left side after landfall. So you can see the intensification is completely different, and we wanted to understand that. And again, second, what is the distance from the landfall when it is intensifying? So that also matters. So taking this, we carried out number of different studies with different scenarios. You can see here, basically there are different test scenarios, and these test scenarios represent the intensification duration, how they intensify, and also in addition to this test scenario or numbers, if we associate some wind speed, it will represent what kind of cyclone is basically affecting. So that study was done. You can see here like A10 is basically cyclone category A, or the scenario A, with wind speed of 10 meter per second. And similarly, if we look at 30, it is 30 meter per second, 60 means 60 meter per second. So we, 60 knots, that is 30.9 meter per second. So looking at these scenarios, when you analyzed, we found that these parameters have significant impact. And where the cyclone is going to be intensifying, that will make, or that will decide what will be the eventual surge, or what will be the extent of damage that may occur. So understanding these processes are very, very important. So this, again, detailed work can be understood from this paper, which was recently published in Climate Dynamics. And I'll not go into details of that due to the shortage of time. However, the work doesn't stop there. We also try to understand how this flooding scenario is going to change in future. So it is already mentioned that we can consider, let us, RCP 4.5, which is a moderate scenario, and RCP 8.5, which is the extreme scenario. So they can be represented by increasing the wind intensity by 7% or 11% respectively. So keeping that in mind, we carried out number of studies. I'm just presenting only one. So we took one typical cyclone, extremely severe cyclonic storm, which was having landfall at Puri, and we wanted to understand what is going to happen at Paradip. So looking at that, we found that in the normal scenario, in the current state, this will be the flooding. And if we look at the RCP 4.5 scenario, the flooding is going to increase again substantially. And if we look at the extreme condition, that is RCP 8.5, the flooding is going to extend substantially, very, very large, extending to large region. So this kind of analysis are required, and we need to have this so that we can be prepared for future scenarios or future conditions, so that accordingly our facilities or our developments can take place. So when I'm talking about the facilities and developments, we also carried out a study to identify the cyclone shelter locations, and we designed a shelter based on that. So when we design, this is just a small picture, but the required amount of analysis is huge. We did cyclone storm surge analysis, we did tsunami model analysis. We really took all the population data and the coastal zone, what is the water network, water body network, what is the road network. And then as per the National Disaster Management Authority guideline, we also defined how many cyclone shelters are required and where they should be located. So along all the coast, the whole coast of Odisha, almost 485 kilometers and 10 kilometers into the land, we took that stretch and identified how many cyclone shelters are required and where they can be constructed, along with the priority where they should be constructed first. And once we did that, then we also designed most suitable cyclone shelter, so that can really accommodate huge number of people that are going to use at that time. And these details or these reports were given to Odisha State Disaster Management Authority for further use. So the point is the work has to again result in the practical applications or implementation. And another work that I wanted to show is the protection of high-risk coastal installations. When we are talking about cyclones, storm surge, or tsunami that is affecting the coast, there are number of coastal protection measures, but if there is a high-risk coastal installation, they need zero inundation or zero overtopping from these kind of events. So there are number of protection measures, and different profiles are suggested by various authors in the past. But when we tried and tested, all of them were giving some amount of overtopping, which is again not acceptable such kind of high-risk coastal installations. So we designed this, we again with lot of trials, we finally came out with this profile, which we call it as forward backward 2 radius profile. And with that, when we tested, we found that the inundation or the overtopping is completely nil. So some profile might have worked for regular waves or this normal wave conditions, but when it comes to surge, then they may not really work. So they may have to, there might have to be a specific kind of design. So that was also suggested, and a complete protection measure layout was provided to them for implementation. So now this is something which I have talked, but this is hard measure. So there are also soft measures which are implemented. You can think of bioshields or coastal vegetation. So when we talk about coastal vegetation, that means there are a number of plants or trees which can be used to protect the coast. So you basically don't interfere with the natural process of the sea, but you still protect the coast. So that is the best or first advisable mechanism, if it is possible. So that also we started working on, and doing experiments is okay, but doing numerical studies are very, very difficult. So we developed a numerical model where we can simulate such kind of extreme waves. We can also simulate the debris, the floating debris that is going to be carried by this kind of waves, and they are going to affect the coast. That will affect the vegetation, that will affect the structures, and how the forces are going to come. So there is another study which we also carried out, which was published in Applied Ocean Research. So students who want to refer that, they can refer this paper and understand more. Now, having said this, it is not only the surge, we also have to look at the waves. So we did a study to understand the changes or the impact of this climate change on the waves in future. So we analyzed 2 different scenarios. One is near term and one is mid term. And this, we found that there is a substantial change or increase in the wave heights. There is a change in the wave direction, also change in the wave period. So if there is going to be change, we also try to analyze how it is going to change the coastal sediment transport. So we understood how the sediment transport is going to change in the future. And based on this sediment transport dynamics, we prepared the coastal stability maps, whether the coast is going to undergo erosion, accretion, or it will be a stable beach. That means without much of a change. So similar to what was prepared by Central Water Commission based on historical data, we also prepared the future scenarios on a broad scale, of course, but it was prepared and it was published. And this work was published in these 2 journals, which can be referred. Now, once these waves are going to increase in future, how they are going to impact or affect the coastal structures. So we wanted to understand that, and while understanding that, we took 2 different types of waves. One is tsunami and one is storm surge. And here I have given how to define the extreme condition or extreme wave condition for these 2 different events. And once we have such kind of events, mostly tsunami is represented as a solitary wave in this numerical models. And when it comes to storm surge, we usually represent them in terms of focused waves, which are very steep with a lot of focusing of number of waves. So we wanted to understand this because these kind of waves, when they come, they can impact the structure horizontally as well as vertically, because there is already a elevated sea level, and the waves, when they come, they can possibly hit the deck. And if they hit, this kind of damage can occur. And as we can see, this deck can be completely displaced, or it can be partially displaced, or there can be a number of ways the damage can occur. So to understand that, we found that there is no such straightforward expression available to calculate the forces. So with a lot of numerical modeling support and studies, we devised or we derived the force coefficients. CH, basically what you see here is the horizontal force coefficient, and CV is the vertical force coefficient. We devised these force coefficients using which the forces, horizontal and vertical forces, can be computed on this kind of structures. And not only the decks or the flat decks, we have also considered deck with girders. So this basically S and H represent the elevation or the air gap and the wave height. So considering the future scenario, if there is going to be a sea level rise, one can accordingly adjust the air gap. And if there is going to be increase in the wave height can be considered here. And based on these two parameters, and depending on the h/d ratio, one can find out the coefficients which can be applied to obtain the forces. So what we have done, we have developed this kind of formulations for solitary wave. We have also developed this kind of formulations for non-breaking focused wave, which is basically storm surge scenario. And storm surge scenario can be non-breaking on the structure, or it can break on the structure itself. If it is going to break, then we have also devised the equations for breaking focused wave impact on coastal structures. So these are going to be really handy for the coastal engineers, that can be used for devising future structures, or even planning to retrofit or rehabilitate the existing structures for the future years. So these are various work that I wanted to present. And with this, I think I will stop here due to the time constraint. So let me thank also to all the team who have done the work. Without them, I cannot really finish all these different research works that we have carried out in the group. Thank you so much for listening. Professor Prasad Bhaskaran, I will be happy to take some questions if it is there.
Yeah. So thank you, Professor Manas Ranjan Behera. It's an excellent and very informative talk actually. And what I understand is you have provided very focused points, new insights, and some of the important research areas that has to be explored for storm surge studies, in particular for the climate change. So overall, the presentation was really nice. Actually, it was very informative. You started with coastal vulnerability and highlighting on the different stressors like tsunamis, storm surge, flooding, cyclones, sea level rise, erosion accretion patterns, the wave impact, and overall its effect on the coastal infrastructure. And it's very important that the cyclone generated storm surge and its impact along the coastline has also been covered in your presentation. The other important area which I found very interesting in your presentation was about the wind stress parametrization. You have actually talked about its importance in cyclone modeling. In particular, actually, you mentioned about the aircraft measurements.
Yes.
Being conducted during cyclone to come out with a relationship, of course, to formulate a relationship between the CD, the drag coefficient, at very high wind speeds. So that was really interesting to see that. And then you talked about the wave boundary layer model for storm surge modeling as well as for the storm waves. And its importance in capturing the significant wave height and the total water level elevation. So these are actually very, very important contributions. I think it's really a good contribution that you have made, this wave boundary layer model, because I think this area has to be a little bit more looked into more in detail. And you also mentioned about the pre-existing wave climate and its role in modifying the sea state. And in particular, that there are some improvements that you're seeing in the wave direction by doing this, actually, by incorporating the pre-existing wave climate in the model.
Yes.
And also, you actually showed about the IWD model, actually. IWD model, and then you compared that with the and its computational efficiency as compared to the wave boundary layer model.
Correct.
That is really good, actually. It is very good that you're able to optimize it. And then you discussed about the flooding scenarios in future, that is along the Paradip coast, considering an extremely severe cyclonic storm making a landfall at the Puri coast. I think that's very, very interesting to see that part. And also you talked about the cyclone shelters, the design of the cyclone shelters, and also the planning for the Odisha state. I think we need to do this similar type of thing again, in particular actually now for the western part of India also, because west coast of India actually is receiving in the recent decades more number of extreme cyclones, which never happened in the past. I think now this is a very important topic, this storm surge and its impact on the coastal infrastructure. Also, you mentioned about the protection of a high-risk coastal installation, that is by using the FB2 radii profile. I think, of course, that is a very innovative design, what you have shown actually, by giving a curvature for the crest of the structure. Then you talked about the extreme waves, its impact on the deck, and the solitary wave impact on the coastal structures. Overall, the presentation was very wonderful presentation. It was very informative, and I'm sure actually that this will actually give inspiration to the young researchers and the students basically who are actually going for higher studies and PhD. So really wonderful presentation. So let me see, actually there are some questions that is being in the chat box.
Yes, sir. So thank you, sir. Thank you for summarizing. And I would like to quickly mention that I wanted to leave some pointers so that the students who are working in these lines, they can actually take some of these areas and they can possibly proceed. There are a lot of scope to work in this area.
Yeah, that's true. That is very much true. Yeah. So there are I think a couple of questions in the chat box, but before I go into that, I have actually noted down some few questions from my side actually, which I just like to discuss with you. Now we know that in this Arabian Sea, if you look into the data, the recent decades, the ocean heat content, especially the ocean heat content, it is basically increasing at a very steady rate actually, as compared to that of, and especially that is the deeper part of the Arabian Sea. So what are your views like about this in terms of cyclone intensity and the development of cyclonic systems in the west coast of India?
As you very well know that the threshold for the cyclone genesis, we have been telling that it is 26.5 degrees. And we are, although it is increasing, the ocean heat content is increasing in the deeper part of the Arabian Sea, but gradually it is also affecting the surface. So as the ocean heat content, overall, all these things are the energy content. So ocean heat content is the energy that is going to be there. So once it is beyond certain threshold, the number of cyclones that we are seeing along the Arabian Sea are going to be suddenly increasing. And although right now we are not giving much of thrust or focus to the cyclones or the cyclonic impacts to the west coast of India, then all of a sudden we will have to work on that. So I think you are right. We can start focusing on that right now before, which is necessary as a preparedness exercise.
Yeah, that is very true actually. And also the other point is, like when we look into the western part of India, unlike the east coast of India, we have very high tidal ranges actually, especially in the states like Gujarat and all. And maybe in the future actually, when we have very intensified storms that are developing in the west coast of India, it can have a very significant impact actually along the coast.
Exactly. Yes.
So I think some of the major cities which are on the west coast of India also is we need to actually make a detailed study of that. How
especially people will be interested to know what's going to happen to Mumbai, which is basically a low-lying city.
Yeah, exactly. Because Mumbai is basically the business capital actually, and we need to actually have a very the last few cyclones that has happened in the western part of India, Mumbai was also affected because of that.
Correct.
Yeah, and one of your presentation you have actually shown about the third order best fit, actually the quadratic fit actually, that you connected the CD and the wind speed.
Right.
So that by looking into the graph, I just recalled one of the discussions actually long back actually. There were some earlier studies actually by this the Office of Naval Research from USA. So they had actually, I was looking at a similar type of figure which they made at that particular time. So they have categorized this wind speed into 3 categories. That is the weak, moderate, and very high wind speed. So what they not observed is that when we take the moderate wind speed in the category of the moderate wind speed, at least a mathematical fit actually we can define a mathematical fit up to some degree of approximation. Of course, it is not exact again, up to some degree of approximation between the CD versus the wind speed. But when we take extremely low wind speed and very high wind speed, what they found is the scatter is very high. The degree of scatter, it goes up. So actually, when we are showing that figure, actually, have you considered the outliers also? Outliers means some of the points, or it has been filtered, whether the data was filtered or whether it was the actual data which is being used actually.
No, it is the actual data that we are using.
Okay.
And possibly we don't have this too much of scattering, and especially we saw some scattering, if not too much, some scattering in the high wind speed. But when it comes to low wind speed, we did not find that much scatter because we did not consider less than 30 meter per second wind speeds in this study. So mostly
that means you're not considered less than 30 meters per second.
Yeah, mostly whatever we have considered we have considered number of cyclones. So in that cyclone, in the wind field, the bare minimum wind speed that we considered as 30 meter per second. So that's why we did not possibly capture that scatter what you are referring to. On the higher wind speed side, we did observe, but whatever we have data, everything was considered for the analysis. And possibly the scatter is slightly less because we have considered the process in the wave boundary layer model. The physical process has been captured here, and that was not the case in the earlier stage. So that's why possibly we have got some improvement.
Okay, fine. So my last question actually is about it was the last slide which you are showing about the coastal protection, the protection of high risk, basically the structures that you're talking about. So you are given a curved shape actually. So the curved shape basically will help in controlling the overtopping. Basically the overtopping will be controlled by using that particular shape. So yeah, so this is basically what it is doing. It's not allowing the water to come on the other side of the breakwater.
Correct.
So it basically spills on the offshore direction. But what about the armor unit material that you're using here? Whether this armor material
units, we are using the same basic formulation what people are using, the Vandermeer's formula or Hudson's formula. That same way we are also designing this. But the only difference is the armor units here, because this is not a wave, or there is not, it is only a surge which is going to just ride on top of this. So the roughness is going to really matter. So that way the armor unit is supposed to be sufficient enough if it is designed for the extreme wave condition. But when the surge goes up at this level, at the crown level, this overtopping needs to be arrested. And for that, what we finally understood that if we can really revert the process or revert the surge quickly backwards, then it will be thrown back into the sea instead of overtopping. So we tried to work on different combinations with the radius, and then finally we found that at this optimum level, the surge is going to be quickly turned back, so that the energy is now having a direction towards the sea. So it will be thrown back into the sea instead of overtopping. And I would like to just mention as a kind of note that this is not a curved seawall. This is the crown wall we have designed. Now, if the same structure we are taking as a complete seawall, then we might have to just relook into it further.
Okay, this is very interesting actually, very interesting. Yeah. Okay, so now let me go to the chat box. I think there are some couple of questions. I'll just read out the questions. I think the first question is by Dr. Satish Shenoy sir actually.
Okay, thank you, sir.
So the question is why tsunami waves are considered as solitary waves?
Yes, sir. Actually, this is an approximation. We know that solitary wave doesn't have a trough. Tsunami obviously will have troughs, but typically when we see tsunami with a very long wave profile, the wave can still be approximated as a solitary wave. And when they come to the coast, the peak, when the solitary wave is simulated in the numerical model or even the plumes, So when they come to the coast, they will basically reduce in their length and the height is going to increase. So invariably, they still represent the basic characteristic of the tsunami impact. So that's why still people represent that as a solitary wave. But technically, tsunami will also have some trough, but not the exact like what we are representing that as solitary. And especially when what happened during this 2004 tsunami, we basically got an N wave type tsunami. So N means it will have a crest, it will have a trough. So if the trough comes first, the scenario is going to be different. If the crest comes first, that will be also different. So yes, these studies are required, but most of the times as a starting point, we represent the tsunami as solitary wave, but not necessarily. We can also represent them as an N wave kind of profile. That's also being done by a lot of researchers. Even I have done it during my PhD.
Yeah. So
thank you, sir, for the question.
Yeah, thank you. Thank you. I think there is one more question. I think there is a last question. It is by Umakanta Pradhan.
Okay.
So the question is, what is the impact of IOD, Indian Ocean Dipole, in cyclone formation?
Okay. So maybe that is slightly difficult for me to answer, but still I'll try, because whatever basic I understood from IOD or some knowledge that I have. So yes, there will be, it is as Professor Bhaskaran initially asked, it's all about the ocean heat content. So if IOD is going to change the ocean heat content and the overall heat pattern of the basin, then it is going to affect. So I don't really know exactly how it is going to happen, but there will be impact. We have been talking about ENSO, La Nina, and IOD, everything, but it's all about the ocean heat content, how that is being affected by this long-term processes or IOD, if we tell. So that is going to affect. So I think right now I can only tell that much in terms of IOD impact.
Yeah, I think there is one more question. Actually, I think it has just now come. It is also from Dr. Satish Shinoy actually.
Yes, sir.
So the question is there a parameter relating the wave crest and length to classify the wave?
Okay, to classify the basically tsunami.
Classify the wave crest and the length.
We have Orsel's number, so that usually we use.
Yeah.
And with that we can classify the tsunami. But again, it depends. If we talk about N wave type tsunami, then we don't have as such any parameter to define that. We only have that for the solitary waves.
Yeah.
So that is something I think we need more work and more research to be done. Right now we have only that Orsel's parameter which defines this kind of waves.
Yeah, that is right actually, because I think the Orsel's number is very important actually when we you can say it is one of the limitations of the linear wave theory, because the linear wave theory we cannot use it in the extreme shallow waters.
Correct.
We have to go for, I think,
we have Boussinesq theory.
The Boussinesq theory, or we have to go for the higher order Stokes theory.
Right.
I think there the Orsel's number actually will be very much deterministic in that case, in that particular thing.
But so far I haven't seen any work which has predominantly done in this area. So that is actually another pointer what Professor Shinoy sir has said, that some work can also be done in that line. Thank you, sir, for this question.
I think, okay, let me see. There are no more questions actually. There are no more questions in the chat box. So, so on behalf of the Ocean Society of India, I thank you very much, Dr. Professor Manas Ranjan Behera, for this wonderful talk. It was really informative, and we would like to hear more talks from you in the future. So thank you very much.
Thank you, sir. Thank you, sir. And I would like to thank Satish Shinoy sir and Umakant Pradhan, both of them, for the pertinent questions that they raised. So I'm sure all the audience, all the listeners are benefited from this talk. Thank you so much. And thanks for the opportunity, sir.
Thank you. Thank you very much.
Thank you, sir.